All right, let's talk about force diagrams. Force diagrams can be incredibly helpful for taking a very complicated situation and making it very easy. So let's take something like a pirate ship, right? It's on the high seas. And inside of that pirate ship, well, of course, we have to have a pirate. So here's our lovely pirate. And, well, any old pirate is probably pretty good at taking some treasure. So here's his treasure. He's got a Jolly Roger flag, and it's kind of a cloudy day on the high seas. But there's still lots of lovely fish in the water. This is what we're going to try to draw a force diagram for. So the first thing we did is we are going to draw a picture. And we've already done that. Here we go. It's our pirate. Now, we're really interested in the pirate ship, I think, for this problem. Maybe we want to know something like, what's the buoyant force on the pirate ship? So we have to ask ourselves, are all parts of this really that important? And probably not. The clouds are probably not important. The fish are probably not important to answer the question of, what's the buoyant force on the ship? So what we need to do is we need to define the system. And we will do that with a dotted line. So the advantage to defining the system is to tell everybody, hey, this is the thing I'm actually interested in. You can ignore all of that other stuff. So we can ignore the clouds and we can ignore the fish, and they don't really mean anything. And the other advantage is that it takes everything inside of our system and it's going to make it one thing. So it is no longer a boat and a flag and some treasure and a pirate. We are now just looking at one solid thing in the middle. And once we have the system, we're going to draw a dot at the center of gravity. We want to try to make this as simple as possible, and a giant pirate ship is not going to be very simple. But if we look at where perhaps this middle of all that mass is, which is the center of gravity, and we kind of just say, what if this whole big complicated ship is really just a dot right here? Wouldn't that make it so much simpler to think about the forces? So that's what we'll do. And from that dot, we will draw force vectors. And we're drawing them from the center of gravity dot. So on this, because this boat has mass, we know that there is going to be a force of gravity on the boat by the Earth. And we know that there must be some kind of force that is pushing back up on the boat. Specifically, we would say that that is the buoyant force on the boat by the water. Don't worry about the buoyant force too much. We're not going to run into it very often. But it is what keeps you afloat. Then the last thing that we want to do is we want to look and we want to add congruency hashes. For the equal forces. So any forces that are going to be exactly the same magnitude, like in this problem, since there's one force pulling us down and one force pushing us up, the amount that the force of gravity pulls down must be the same as the amount that the buoyant force pushes up. So they must be equal to each other. And you guys use congruency hashes like this in geometry, so hopefully this is not too unfamiliar. Now let's practice drawing some force diagrams. By the way, force diagrams are also called free body diagrams. So the first one we're going to do is a book on a table. So step one, draw a picture. There we go. That's my book, and that's my table. And now I want to define the system. So I'm really just interested in the book on this table. The center of gravity of the book is right about there. And I know that the force of gravity is pulling down on the book. It's by the earth. And then that table is pushing up. And any kind of pushing from a surface we know is a normal force because of that mathematical term normal, meaning perpendicular to. Now this book is not sliding across the table, so there's no friction, there's no ropes attached to this book, so there's no tension, there's nobody with a hand pushing on the book, so there's no applied force. As far as I can tell, these are the only two forces acting on this, and since there is one force pulling down and one force pushing up, those two forces must be equal to each other. So we'll add the congruency hashes. Ta-da, we are done. Let's do another example, a book on a hand. So first we need to draw a picture. So we'll have a bit of a horror hand right there. It's not too horrible. Now there's a book on this hand, so there's the book. And now I need to define my system. So yet again, I'm really only going to be interested in the book. So we'll draw a dotted line around the book. The center of gravity of the book is probably right about there. Since this book has mass, I know that there is a force of gravity on the book by the earth. And this hand is pushing up on the book. So we could say that there is an applied force on the book by the hand. Now this book is not sliding on the hand, so there's no friction. There's no surfaces involved, no walls, floors, tables, so there's no normal force. There's no rope, so there's no tension. I think this is kind of it. So since there's one force pulling down and one force pushing up, those two things must be equal to one another. Lastly, let's do a book hanging from a string. So here's a string hanging down, and it is holding on to this book. So we will draw our system as the book. There is the center of gravity of the book. And yet again, because this book has mass, we know that there's Fg on the book by the earth. And there's a rope pulling up on this, so we know that ropes exert tension forces on the book by the rope. No hands this time, so no applied force. No sliding, so there's no friction. No walls or tables or floors, so there's no normal force. Yet again, I think we really only have two forces here, and one of them's down, one of them's up, so they must be equal to one another. Now, going through and asking yourself, those questions like, is it sliding? Is there a rope? Is there a hand that's pushing on it? Those are always good questions to ask yourself because that'll help you identify what forces might be acting on an object if you're not totally sure what's there. Now we're going to do a lot of stuff with forces this unit, but more specifically, we're going to be trying to exclusively look at situations where we have balanced forces. So balanced forces is when all the forces acting on an object sum to 0. So because we know that if things are in different directions, we give them positive signs and negative signs, we would hope that when we add up all of the forces, those positives and negatives would cause us to end up having a total amount of force that is equal to 0 for balanced forces. And if we look at those three examples that we just did, because the force down was equal to the force up, that's what's happening. So we have three examples of balanced forces right here above. Unbalanced forces, as you can probably guess, is when all forces acting on an object do not sum to 0. We will be looking at situations where there is perhaps a larger force to the left compared to the force to the right. There is a larger force up than there is down, but we're going to wait until Unit 5 to do that. So next unit, we'll get to unbalanced forces. The last thing we're going to do here is we're going to try to draw some more force diagrams for practice. So let's draw the force diagram for a kick disc at rest. Now, if you don't know what a kick disc is, it's really just a round piece of plastic. Well, it has a motor inside, and the motor blows air out the bottom so that this kick disc can kind of float along the floor on a bed of air. So right now, this kick disc is just at rest. So if I make my system the kick disc, I think to myself, well, the kick disc has mass, so there is a force of gravity on the disc by the Earth. It's sitting on the floor, so the floor is a surface. It must be pushing up with a normal force on the disc by the floor. But this disc is at rest, so there's no sliding, so there's no friction. There's no ropes, so there's no tension, and there's no hand on this, so there's no applied force. So I think that this is all the forces that we have. So the fact that there is one force down and one force up means that those forces must be equal to one another. Let's think about another kick disc. This one is now going to be moving at a constant velocity. So if we kind of think about this snapshot of the kick disc moving at a constant velocity. So you can imagine in your mind, maybe the kick disc is moving to the right. We now want to draw the force diagram for this kick disc. So we will draw a dotted line around the kick disc, and we will say the center of gravity of the kick disc. And because this kick disc has mass, we know that there is a force of gravity on the disc by the Earth. And this thing is on the floor, right? So the floor has to be pushing up, so there must be a normal force on the disc by the floor. Now this thing is sliding, right? It's moving at a constant velocity. But the cool thing about a kick disc is it's got that motor that blows that air, and so there's like a bed of air between the kick disc and the floor. So we really don't get any friction when this kick disc is moving. So I don't need an arrow to show the force of friction. And well, right now when it's moving at a constant velocity, nobody's pushing it anymore. We already pushed it, right? Like we pushed it to get it started, but this snapshot is when the thing is moving. So there's nobody's hand on this kick disc. So there's no applied force either. There's actually no other forces that we need to add onto this force diagram. So we can just add our congruency hashes because one force is pointed down and one force is pointed up. We can call it a day, which is really kind of strange because it looks like the force diagram for the kick disc at rest is exactly the same as the force diagram for the kick disc moving at a constant velocity. But actually, it's not that weird. This demonstrates Newton's first law. Newton's first law is trying to describe to us that as long as we have balanced forces, so the forces up is equal to the forces down, forces to the left is equal to the forces to the right, we will be at rest or moving at a constant velocity. The force diagram is not going to tell you how this thing is moving because the force diagram for things at rest and things moving at a constant velocity looks exactly the same. So whenever you guys see something moving at a constant velocity, you need to know that your forces all have to balance one another in order for us to abide by Newton's first law. So what conclusion can we draw from the above force diagrams? Objects at rest and objects moving at a constant velocity have balanced force diagrams. And just for good measure, we can remind ourselves that this is really trying to describe to us Newton's first law. All right, very good.